Okay, hello again. Tonight we're going to talk about interstellar intruders. These are things that come from the outside and either pass through or might affect our solar system. And if they pass through, then they exit the other side and they're gone. We have no control over them. We don't initiate them. They come in from outside. So we'll take a look at that. So the reason why I'm doing this particular presentation, and it's going to be a short one, is I was working on something else, which was 21 centimeter hydrogen line. I was doing an antenna, a drive mount, post-processing software to create radio images, and then produce a Broward Astronomy presentation on it. And some of the things that I ordered this week were delayed. They were supposed to be on 2-day delivery. That turned out to be 4-day delivery, which, man, I missed it. And the second thing is I ordered some motor shaft couplers with the wrong dimensions, which induced another delay. We'll talk about that in the future. Instead, somebody had asked me to talk about the Threeey Atlas interstellar comet. And so I said, okay, well, I'll talk about that, but I'll extrapolate it out for not just that, but for a number of things in that regard. So on the right, you see the sections of a cone, or conic sections as they're called, and a circle, that's kind of an orbit around something, an ellipse, that's kind of an orbit around something. A parabola comes in, goes back out, but if you expand a parabola so that it's both halves of it, you're back to an ellipse. But the one that we're interested in here is something called a hyperbola, or a hyperbolic course, or a hyperbolic trajectory. And this is where something comes in, goes around a heavy gravitational object, and then slings back out. So things that come into our solar system then go back out. Our solar system has multiple debris fields: the asteroid belt, the Kuiper belt, the Oort cloud, and we have asteroids that are either big things or microscopic things. And the big things can either be solid rock, solid metal, rocky metal, or they can be rubble piles, just things that are loosely held together by static electricity and gravity. You can have these things that are comets. They have ice on the surface. When they encounter the radiation pressure from the sun, they make comet tails. They might have big tails, small tails. As they are on the outside of our solar system, no tail. And then as they get closer to the sun, the tail switches on. If they do that enough cycles, the tail can get less and less. And eventually you'll have something that's a dry asteroid that was maybe 1 million years ago a comet, but is now a dry asteroid. Still goes around the sun. Some of these things have potential to be Earth-Moon orbit crossing or affecting. These are the ones we have to watch out for that, maybe in a far-off future might hit the Earth or the Moon, but not right now, but we have to pay attention to them. And then we have this category called dwarf planets. Pluto's a dwarf planet, but Pluto doesn't care what us silly humans call it. Pluto's big enough to have 5 moons. The Earth, despite being much bigger than Pluto, only has 1 moon. Which one's more like a planet? If you're large enough to be round and you're going around the sun, I think you're a planet. If you're not big enough to have cleared out your orbital debris, then, you're a dwarf planet. Jupiter, the biggest planet in the solar system, has Trojan asteroids that sit in 2 of its Lagrange points. It has more orbital debris than the orbital path of Pluto, but Pluto is still a dwarf planet and Jupiter is still a full-fledged planet. Things that orbit planets are called moons. Sometimes they're original from the formation of the planet. Sometimes they're captured, or they strayed and got too close and were pulled in by gravity. So we now have 3 interstellar debris objects have made it into our solar system. One of them is on its way in towards the sun. It'll slingshot around the sun, and then it'll go back out. The first one we officially identified was ʻOumuamua. It's not that big. It's 750 feet by 115 feet by 115 feet, kind of cigar shaped. The next one was something called Borisov. That's 2I. That's the second interstellar Borisov. It was about 1,640 feet, kind of roundish, so we didn't have other dimensions for it. Now we have one that's bigger and is moving even faster, and it's kind of potato shaped, but we don't have exact measurements on it. 16,400 feet end to end. Think about that. That's a couple of miles. And it's also moving faster than any of these previous objects. And it's still on a a hyperbolic course, so it's just passing through the neighborhood. 3i is large, but it's not the potentially largest thing that could pass through the solar system. If it's on its way in and it's going to go past the sun and swing its way back out, and it doesn't cross Earth's orbital path when we're in that vicinity, then there's no threat to Earth. The velocity of this thing, last time we measured it, was 68.3 kilometers per second. That's moving. The fastest rocket we've ever launched was New Horizons using an Atlas V to get out to Pluto in only 10 years. And that was only doing 16.26 kilometers per second, less than 1/4 of what 3i is doing. The fastest probe that mankind has ever experienced was the Parker Solar Probe, and that was only going 191 kilometers per second, which is faster than 3i, but that's after it went around the sun on a long elliptical orbit several times. That's how it got to be going so fast, not because we had the technology to make it go that fast from Earth. We don't. So if somebody says, well, why don't we launch something from Earth and have it land on 3i Atlas, and we can do studies, and as it leaves the solar system, we'll have like a Voyager 3 that will go out into the galaxy, or at least between the stars, and we can talk with it. The problem is we don't have the technology to catch up with it before it leaves the solar system. Good idea, but nope. So what other things can we encounter? And that's where the intruders come in. They're officially referred to as rogues. But all these things that come in from outside the solar system and either hit some planet in our solar system or hit the sun, those are all this thing called rogues. It's just some of them skip through, some of them don't. So anything that's flung out from another system or ejected from another system and goes free roaming in space is referred to as a rogue. So a planet that is no longer orbiting its parent star because it got kicked out for some reason is now a fairly large rogue. Think of something the size of Venus or Earth that gets kicked out of its solar system and is now just booking along between the stars and happens to encounter our solar system. We can spot something like that coming from a distance if we're looking. If it happens to be something like a Jupiter that's a little bit farther towards being a star and it's a brown dwarf rogue planet, then it's harder to spot visually. So we'll have to look at that in infrared. So we can't just look at the sky in visual. We have to look at it in other wavelengths in order to spot some of these other types of rogues. And if a moon that was previously orbiting some distant planet in another solar system splits off from its planet, it's no longer orbiting its parent planet. It's now a rogue. If it happens to be a large moon that was orbiting a large planet, and now it's spinning out there as a rogue between solar systems, how would you know a rogue planet from a rogue moon? Size is not a characteristic you can use because you don't know what it used to orbit. If it orbited a star, it's a planet. If it orbited a planet, it's a moon. But how would you know? If this rogue happens to be a moon or a planet and it's not emitting lots of infrared, we'll have to wait until it gets close enough to our sun for it to reflect light off of it for us to see it. Otherwise, it's just a black spot floating in the sky. It's hard to see those unless they're producing their own heat infrared-wise. Stars, if you have a multiple star system, a binary or triple star system, they can go on complicated orbits, and one of the two or three can be flung out from the system. So you can have a rogue star free roaming in space. Now, obviously, if it's producing light or if it's producing radio output, as stars do, then we can spot that from a distance, even if it's a small red dwarf star. So I'm less concerned about those. We have spotted rogue stars, but they're not aiming towards us. They're either aiming away from us or they're crossing the path of our solar system with no encounter expected. But you can also have stellar explosion fragments. This is, let's say, a coronal mass ejection. You've heard about coronal mass ejections coming off of our sun, and you've heard about them being moving out into our solar system and maybe encountering Earth. Where do they go from there? Let's say a coronal mass ejection, a CME, comes off of our sun and the Earth is not there at the point where it crosses the orbital path of the Earth. So it goes out in the solar system. Where does it go from there? These expulsions or stellar fragments, they're going at very high speeds and they don't have all that much mass. So they're not going to be dragged off to Pluto or Saturn, Jupiter or Saturn. They're going to leave the solar system. So you can have a stellar expulsion or a fragment that can travel between stars. Have we ever seen one of these? Nope, they're only theoretical. But yeah, you can have moving between stars. And then there's always what if you have two black holes that are zipping around one another and they go so fast that one of them gets flung out rather than the two black holes merging? You can now have a black hole zipping through open space. How do we know where they are? If they don't have any debris around them, they're not going to be producing any infrared. They're not going to be sending out any photons either in light or radio or X-ray. How will you know where they are? Because they will have such a high gravity field, they will induce what is known as gravitational lensing, or they'll bend the light of the stars behind them and we'll spot this distorted area moving across the sky. So that's how we'll know. Or if they have debris around them, they're consuming something, there'll be an infrared glow from that or a radio glow from that. There can be black holes running around out there too. So should we be afraid? It's simply a matter of probabilities. Space is enormous. The Earth is minuscule. They're not looking to come and get us. They're not targeting the Earth. Although if somebody has really advanced technology, they could do that. But why not just do it with an asteroid in our solar system if we really want to attack Earth? But so far, none of those things have done that. The one that wasted the dinosaurs, we don't have precise information as to where it came from. The current prediction is it came from our solar system's Oort cloud a long time ago during the early stages of the solar system. That's the kind of thing that can give you a bad day, can be an extinction level event. But most of these things that are rogues, they're just going to slingshot. They're going to encounter a star system. They're going to encounter a high mass object like a Jovian-sized planet or a star, and then they're just going to scatter. They're going to slingshot, scatter. Or if they do get captured by a large planet or collide with a star, hey, that takes the probability of it encountering Earth to zero because it's not there anymore. A solar system is large. Earth is tiny by comparison. There's a lot of open space. Think of it as there are meteors that hit the Earth on occasion. The ones that encounter populated areas or high population densities are few and far between because the Earth has a lot of ocean space. And if it doesn't cause a tidal wave, a meteor can land in the ocean and nobody saw it happen. You don't notice it. But there's a higher probability that these rogues will pass through the solar system at high velocities, and therefore they'll just wing their way through, go around a large planet or go around the sun and never seen again. Once they leave, their orbit is hyperbolic. It's not orbiting the sun, so it's not coming back anytime soon. If something is going to be in the solar system such that it is going to be directly affected and go into orbit, it's going to be the sun, Jupiter, Saturn, Uranus, or Neptune, and it might just slingshot it into a long elliptical orbit, or it might capture it or collide with it, which reduces the probability to zero. What we don't want to have happen is anything that would collide with the Earth or anything that would collide with the moon, where it might blow off something that will eventually collide with the Earth. Should we be on the lookout for these kind of things? Absolutely. The best approach to dealing with something is to know about it. Now, how would you spot it? Well, you can start with wide field observing, like the Rubin telescope. It can do 3 degrees by 3 degrees, 3 degrees by 3 degrees, and come back to the same area every 3 days. So it can look across big chunks of the sky. Not the whole sky all at once, but big chunks of sky. In its first observing, the Rubin found 9 trans-Neptunian things. These are objects that are in the orbit out past Neptune before the Kuiper belt. It found 9 of them the first time it looked out and towards that direction. That's just one small spot of sky 3 degrees by 3 degrees. So once you detect something moving, then you assess its orbit to see, is it going to encounter the solar system? If it's moving kind of in a hyperbolic or straight line course, it's probably not going to encounter the solar system at all. If it's moving with a little bit of curve to it, it could be hyperbolic around the sun. So you want to plot the potential targets. Is it going to be the sun, planets, or the moons? Judge the size, its density. Is it a rubble pile? Is it rock? Is it metal? Is it rocky metal? And then the orbital, the rotational characteristics of it. Is this thing, flipping around, or is it stable? And the way you do that with the Deep Space Network, with NASA's radio communication system, and you use it for radar. So you'll pick something like the Allen array as your radio transmitter, and you'll have a very focused beam towards this object, and then the radar will bounce off of it and be picked up by the big dish in California as the radar reflector. They're judged characteristics. That will give you a better understanding of its size, how dense it is, and what its radio reflectivity is, as well as you watch it for a while and see how it rotates. So once you've judged all that, now you can determine it's there, it's real, we have an orbit, we can predict where it's going to be, next Thursday night. And now you can have other observatories, the visible one, pinpoint it, maybe gonna zoom past the Earth close enough, you might even see some detail on it. But in the case of Threeey Atlas, it's going by too fast. We couldn't put a rocket together that would slingshot up enough speed to get to it before it leaves the solar system. So if it's small and it's just passing through, we can use that to check our contemporary technology for observing, planning for, let's say it did happen to hit something, and then what would we do? The last time we watched something else get hit was the Shoemaker-Levy 9 comet as it impacted Jupiter. So if it's not the Earth or the moon, then yeah, we've already had experience recording impacts on large Jupiter. And yeah, Jupiter took some bruising from that, but didn't really change anything. If it's going to affect the Earth or the moon, which could indirectly affect the Earth, and we predict an impact, you probably heard of the Federal Emergency Management Agency. If it's planet-wide, then maybe the UN would need an international emergency management agency, because if it creates a tidal wave, you're going to have population centers that might get destroyed. You're going to have populations that might be uplifted and have to move quickly or recover. And that's going to be many, many billions of dollars for the beat. And if it's an extinction level event, if it's going to waste the Earth and we know about it far enough in advance, maybe we find out how to migrate to, get a colony going on Mars with more enthusiasm, more money. Maybe we find out, well, it's going to slosh over the Earth for a while, but eventually after, 60 days, it'll stabilize. Maybe we build some underground shelters with the appropriate pumps and such. Or maybe we go Noah's Ark style until we actually pay attention to this stuff, be on the lookout for it. We won't know how much we have to do. So in summary, there's a lot of stuff out there in space, from tiny to massive, rocks to stars to black holes. Keep an eye out for these rogue intruders. And if you spot them, evaluate what their effect is going to be on the solar system. If they're just passing through, have fun watching them, because they're going to zip through and zip back out again, never to be seen again. If they're going to be interacting, what are they going to interact with? How do we judge that in advance? And if we have to prepare for some sort of recovery, take it seriously, because it may be how we survive as a species. And then what all these sorts of things are. It's Threeey Atlas and not One-Eye Atlas. We already have two on the books. Two is Borisov and one is ʻOumuamua. And then if you're interested, what is that Parker Solar Probe of which he spoke? Oh, there you go. There's some information. And New Horizons? Is that a newer New Horizons? No, it's the one that's already gone past Pluto and headed out into the Kuiper Belt. And then if you've forgotten the Shoemaker-Levy 9 and how it impacted Jupiter, there's that. Okay, I was hoping no one would come away with nightmares from the rogues that are going to hit the Earth, because space is big and Earth is small.
Okay. I got nothing to say.
Or
well, I did have, are we depending on professional people to see these road things, or are we, like things that we can't see as amateurs? Or are we depending on amateurs to see the weird things out there?
The correct answer is yes. Okay.
Both.
If it happens to be an asteroid or a comet, there are individual amateur astronomers that do imaging that have spotted these things. In fact, Shoemaker-Levy 9, the Levy is a guy whose last name is Levy, and he has I think it's a 10-inch or 14-inch or something like that, Newtonian telescope that he used to take pictures of the night sky to try and spot new asteroids and comets. So yes, there are amateurs that can spot these things if they're up close, if they're not in the deep infrared, and if they're not so far out and tiny that we on the ground we just don't have the ability to spot them. But we do have things like professional observatories now, like the Vera C. Rubin Observatory in South America, that can spot these small things moving across the sky and can, over a couple of nights, come up with a basic orbital trajectory for them. And then you can pass that along to other professional astronomy observatories in other wavelengths like infrared or even radio, and observe them. So the answer is yes, there's all kinds of professional and amateur observing going on to see all these different kinds of things.
Are we concerned that there may be less professional ones?
When I looked at the NASA budget, yes, I was concerned about that. But the funny thing is, the new U.S. National Science Foundation, in collaboration with the U.S. Department of Energy, the folks that look for nukes or look for, intercontinental ballistic missiles flying around in the sky, they were part of the funding for the Vera Rubin telescope because it takes such a big picture of the sky, it might spot missile launches where we might not otherwise see them. So we spot them in radar, we spot them in visual, and we spot them in infrared. And I'm less concerned once I found out that the U.S. Department of Energy was part of the funding for the Rubin, because if it wasn't, I'm not sure the Rubin would have a long operational life. As I stated before we started recording, the Spitzer Space Telescope observed in infrared, and one of its jobs was to look for infrared things coming up from the Earth, like missile launches. So it was properly funded by the government. And once it no longer had the liquid helium to cool its sensors, that was about 10 years afterwards. It went through a cool down, a warm up, cool down period where it was no longer as sensitive to infrared. And so they moved it out of its Lagrange point to a normal solar orbiting position. And then eventually it ran out of orbital correcting fuel. And so the satellite was turned off, but it still had archives of data that amateurs can use. And one of the things that has happened is the funding for maintaining that archive has moved from where it used to be to another government operated archive of infrared data, which is more likely used for military things, watching, missile launches and such. So I'm glad to see that they moved the funding around the shell game of where do we keep the archive this week? Because those science people like these archives. But the people that aren't as science minded and don't see bigger pictures might go, are we still funding that? Did we turn that satellite off? Why are we still funding the archive? Aren't there better things now? You got to keep an eye out for these things. Okay. I said it was going to be a short one, and it was. And any comments or questions before I stop recording? Hearing nothing.